Hi, good morning, everyone. So we are done with simple harmonic motion, oscillation. We are done, but there are a few questions that you have to complete. Have you completed them? Yes. I think I would have asked you to do only up to question number 16. I have told you to complete from oscillations, and you have done it. Good. You have completed, right? Have you completed the homework questions? Yes. Right. Let's start with a new topic. We'll do a few more questions from this later. Start with the new topic.
So you're 6?
About to fall sick, I think.
On
the way. Astrophysics and cosmology. Astrophysics and cosmology. Right. There is under that the subtopic gravitational field. Gravitational field. So tell me, what is an electric field? A region in space where a charged particle will experience a force. That is what you call an electric field. What is the magnetic field? A region in space where a magnetic pole will experience a force. So what is a gravitational field? It is a region in space where a mass will experience a force. Any place where a mass will experience a force is what you call a gravitational field. So right. It is a region in space where a mass experiences a force. It is a region in space where a mass experiences a force. And the next subtopic, gravitational field strength. Within brackets, simple G. Gravitational field strength. Okay. So gravitational field strength is, now if you're in a gravitational field, the amount of force acting on a unit mass, on 1 kilogram of mass, the force acting is what you call the gravitational field strength, right? It is the force acting per unit mass. It is the force acting per unit mass. Okay. Right? Fine. It is the force acting per unit mass. So gravitational field strength is denoted by G. G is equal to F over M, force per unit mass. Right. Now, listen to me. Now, when you take an object and when you leave it, it falls. Yes? Falls, right? Like. Goes up? Gravity. What is that gravity? Who is pulling this down? The earth. Why? Why? So basically you are telling me the force, the earth exerts a force on this. Correct, no? Yeah. So when you leave it, it falls. Because the earth pulls it down. And that ability of Earth pulling an object down is what you have understood as gravity. No? My question is why? Why is the Earth pulling it down? Magnetic field. So you are saying there is a magnetic effect behind it? Not at all. Why is there an Earth's gravitational field?
Due to its mass.
Due to its mass. Okay.
Because of the sun.
Because of the sun. Sun, no. Sun doesn't get involved in this business. Okay, sun has other business to do this. Guys, do I have a gravitational field? Do I have a gravitational field? Yeah.
No, the Earth's gravitational field pulls you down, right?
So now all of this happens. Now Newton has explained this beautifully. Why does this happen? Like looking at the apple falling, and then he started thinking, why did the apple fall? Why can't it just be there? Why can't it just float? Okay. Now, for us, it sounds like very stupid, but if you think about it, it makes a lot of sense. Okay. Now, if you take the same apple to the space and leave it, it will be just there. But if you bring that apple to the earth and if you leave it, it falls. Why? So this is, he was thinking about it when there was nothing stated about gravity. Okay. So guys, the reason is, so he came up with this law, Newton's law of gravity. Okay. Listen, the reason is, he has explained it beautifully. If you take any two objects, any two masses, there is an attractive force between them. Forget about the earth, really. Forget about the earth. If you take any two masses, there is an attractive force between them. So then you can think, is there an attractive force between these two? Yes, there is an attractive force between these two. You have an attractive force between everyone and everyone around you, and anything and everything around you. You have the ability of pulling it. You are exerting an attractive force on everything that is around you. But it doesn't physically come and get attracted. Why? That force is extremely small. We can do the calculations and see that force between two people of mass approximately 70-80 kilograms or 60 kilograms at a distance of about 1 meter, that Earth's that gravitational pull, that attractive force is negligible, small, extremely small. So that is the reason when they seated together, they don't come and get attached, because that force is too small. Understand? So Newton has explained this. There is an attractive force between any two masses, attractive force is there. That depends on two things. One is, it depends on the magnitude of the masses. He says, this attractive force is directly proportional to the product of the masses. Okay, the bigger the masses, higher will be the attractive force. Understand? So if you increase your mass by another 30 kilograms, and if you increase your mass by another 20 kilograms, then your attractive force will be more. More the masses, more will be the attractive force. And also he says, the force between two masses is directly proportional to the product of the masses and inversely proportional to the square of the separation between them. Inversely proportional to the square of the separation between them, to the distance between them. So that means, bigger the distance, greater the distance between the two masses, lesser will be the force. So if they get closer and closer, the attractive force will also be bigger and bigger. Understand? So now, if it is negligible between two people, two objects, it is negligible. The force is too small. But if you take the Earth has a radius of about 6,400 kilometers and a mass of about 6 into 10 to the power 24 kilograms. I repeat, 6 into 10 to the power 24 kilograms, which is a billions of million kilograms. The Earth's mass. So since it has a huge mass, it can make a significant attractive force on us. Okay, so now we are standing on the circumference of the Earth. We are standing on the circumference of the Earth. You are here. The Earth's mass is concentrated here. This distance between you and the center of the Earth is 6,400 kilometers. And the Earth's mass is, as I told you, 16 to 10 to the power 24 kilograms. Okay. So due to this huge mass, it can make a significant force on you. That force, that attractive force, is what you call the gravitational pull, or your weight. Okay. Your force, the weight acting on you, is the gravitational pull exerted by the Earth. Exactly. So that is the reason, the more and more that you go away from the Earth's surface, the gravitational pull will be lesser. Understand? Why? More and more you are going away from the Earth's surface means you are increasing the distance from the Earth and you. Okay? When you go away from the Earth's surface, then the distance between you and the Earth is more. So when that thing happens, according to Newton's law, the attractive force is inversely proportional to the square of the separation between them. So if you increase the distance between you and the Earth double, then the gravitational field strength, the weight acting on you, will become 1/4. You understood? The force is inversely proportional to the square of the separation between them. So that means if you are at a distance of 6,400 kilometers from the Earth's center, if you go up another 6,400 kilometers above the Earth's surface, if your current weight is 600 newtons, when you do that, you will feel 150 newtons if you go 6,400 kilometers above the Earth's surface. Understood? 600 into 1/4, 150 newtons. You will feel like a 15 kilogram person. Get it?
But then why are you more likely to fall down if you're at a higher elevation?
Meaning?
Isn't that because the Earth pulls you with a greater force?
No.
Then why
What do you mean by high elevation? I didn't get you. What?
why are
High,
you more likely to fall down like the greater your altitude?
more likely
Like
at any height.
you know, like any objects only fall down at a certain height, like due to gravity. I mean, yeah. No, sorry, I don't think any. Yeah, when let's say you're standing on like a table, you're more likely to fall down than if you're like at the closer to the ground level. Like, so isn't that due to gravity? Like you fall down due to gravity.
No,
Like that
it has
was also-
nothing. Now, if you take, now when I said this gravitational field strength will be significantly reducing as you move away from the surface, listen to me. Now, I am talking in thousands of kilometers. The Earth's radius is 6,400 kilometers. I told you if you go 6,400 kilometers above the Earth's surface, your weight will become 1/4. So when you go above the Earth's surface by 10 meters or 50 meters or 100 meters, it won't make a difference. It will be almost the same. So if you just take 100 meters above the Earth's surface, the gravitational field strength will not be different. It will be almost 9.81. If you just go 100 meters or 500 meters or even 1 kilometer, it won't make a big difference. So if you are to see a significant difference, you have to go at least about 1,000 kilometers above the Earth's surface for you to see a difference. Because the Earth's radius is 6,400 kilometers. I'm talking with respect to that, comparing to that. Okay, fine. Write the next subtopic. Newton's law of gravity. Newton's law of gravity. Right under that. The attractive force between 2 point masses. The attractive force between 2 point masses. is directly proportional to the product of their masses. Is directly proportional to the product of their masses. And inversely proportional to the square of the separation between them. Inversely proportional to the square of the separation between them. Okay. So guys, draw this diagram and take it down. If the two masses are M1 and M2,
Actually, Mr. I'm still writing the notes, sir.
if the two masses are M1 and M2, and if the distance between them, if the separation between them is R, so one proportionality is F is directly proportional to M1 into M2. The other one is F is proportional to 1 over R square. Putting both proportionalities together, F is proportional to M1, M2 over R square. And then the proportionality constant is G, which is known as the gravitational constant. So it will become F equals G M1, M2 over R square. The value of the constant G is 6.67 into 10 to the power minus 11 in terms of SI units.
Sir,
Yeah.
so could you go up, sir, for 1 second? I'll take a screenshot of the note. Thanks, sir.
Gravitational field strength. No, sorry, gravitational constant. Capital G is gravitational constant. Gravitational constant. G is gravitational constant, capital G. But the writing has to be wrong. G is gravitational constant 6.67 into 10 to the power minus 11. Uh, 39. Constant number 39. Constant number 39. That is capital G. Yeah. 6.67. Ten to minus. Bro, constant is about this. Restrict that, and put 39. Then you will get G. That is a constant. So it is how it says here. You the sign of constant number 39. So all the constants that okay. Okay. Right. Right. I have a question. Yeah. Yeah. Question 1. Calculate the force between two masses, which are 2 kilograms and 5 kilograms. Separated by 20 centimeters. Separated by 20 centimeters. So guys, F equals G m1 m2 over r square. G is 6.67 into 10 to the power minus 11. M1, M2 is 2 and 5, 2 into 5. R is 20 centimeters, which is 0.2 meters, and that's square. That is 1.67 into 10 to the power minus 8 newtons.
10 to the power minus 9.
Huh?
Yeah.
6.67 into 10 to the power minus 11. The gravitational constant. So this is the reason, guys, I told you to look at the force. 1.67 to the power minus 8 newtons. This force is extremely small to be felt, less than a micronewton. Okay. Right on the next question. Question 2. Two persons of masses 60 kilogram and 70 kilogram are separated by 2 meters. Are separated by 2 meters. Full stop. Calculate the attractive force between them. What's the force? So F equals 6.67 10 to the power minus 11 into 16 to 70 over 2 square. That is how much F equals? 7 into 7 into 10 to the power minus 8. So once again, it's an extremely small force. When you are seated 2 meters apart, the force that is experienced is 7 into 10 to the power minus 8 newtons. That is not big enough for you all to get attracted. Okay, the force is too small. Right on the next question. Mass of the Earth is 6 into 10 to the power 24 kilograms. And radius of the Earth is 6,400 kilometers. Full stop. Calculate the gravitational force. Calculate the gravitational force acting on a person. Acting on a person of mass 45 kilograms standing on the earth. Okay. So guys, now look at this. If you take the earth, it has a radius of 6,400 kilometers. And the mass of the earth is concentrated at the center. So you can consider it to be two objects. One is here with a mass of 6 × 10 ⁻² 24 kilograms. The other one is you, the man, with a mass of 45 kilograms. If you see the distance between their center of gravity, which is equal to the radius of the earth, 6,400 kilometers. Do you understand that? The distance between their center of gravity is 6,400 kilometers. So if I use the equation, F equals...
So depending on where he is also, right? He can be on top of a mountain and then on that change distance.
Do you think there will be a significant difference? What is the height of the mountain that you are talking about?
Mount
100 feet.
Everest.
Okay, what is the height?
I don't know.
Huh? 9 kilometers. Okay, let's say you have gone 9 kilometers above the Earth's surface. Still, the distance will be 6,409.
109.
Okay, so which you can take it as definitely 6,400 kilometers. It is not going to make a difference, big difference, almost no difference. So it's going to be 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 into 45 over 6,400 kilometers means 6,400 into 1,000 meters, that's squared. That gives you the F. How much is that? Are you getting something like 439.7 newtons? Yes. Correct. Now guys, now we have learned from small days the weight of an object on the surface of the earth is W equals mg. Mass into gravitational acceleration or the gravitational field strength. What is the gravitational field strength at the surface of the earth? 9.81. Correct, no? 9.81. So now this person's mass 45 kilograms means if you multiply 45 by 9.81, W equals mg, what are you getting? Wait, can you calculate and tell me? 45 into 9.81. 441. So we got here 439, 440. So that gives you that 9.81 has come as a gravitational field strength based on this calculation using Newton's law of gravity. Okay. So now you should understand that gravitational field strength, which we take as 9.81 newtons per kilogram, that can't be anywhere on the surface of the earth. It can't be exactly 9.81 everywhere in the earth. Reason, I can give you two reasons. One is, guys, if you take the earth, okay, one thing is it's not a perfect sphere. Obviously, no. So it may be, I'm just drawing, maybe something like this. Okay, so for an example, from the center of the earth, if you measure the distance to Colombo, we are here. And if you measure the distance from the center of the earth to London, or if you measure it to this fellow is where? Saudi. Okay. The distances are not the same. It's not a perfect sphere. No? You thought when they made the universe, I mean, when the Milky Way was formed, they perfectly measured and made the Earth. Okay, we have to make it exactly 6,400 kilometers, a perfect sphere. No, right? So these radius are different. The distance to the center of gravity is different. So definitely, then the gravitational field strength in Colombo and London and Saudi and everywhere else can't be exactly the same. That is one reason. Okay. The other reason, now we consider this to be the mass of the Earth to be concentrated at the center. No? That is assuming that mass of the Earth is uniformly distributed throughout the body, throughout the object, throughout the Earth. But not really. It doesn't have a uniform density. Certain parts of the Earth may be denser than other parts of the Earth. Am I right? So you can't expect the weight distribution or the Earth's mass distribution to be uniform. So you can't expect the center of gravity to be exactly in the geometrical center. But anyway, this calculation will give you a very, not 100% accurate value. To a greater extent, it will give you accurate value. Understood? Fine. Right on the next subtopic. Gravitational field strength. Gravitational field strength. Due to a point mass. Gravitational field strength due to a point mass. Okay, let's say, guys, now there is a mass in, okay, there's a mass capital N, and there is a mass 1 kilogram kept at a distance r from this mass in. I'm going to come up with an equation for the gravitational field strength at this point, which is a distance r away from the mass in. Okay. So now, according to Newton's law of gravity, the force exerted is given by F equals G m1 m2 over r square, right? Correct? No? So which is F equals. Now this F is what I'm going to take as G, the force per unit mass, G. That is equal to G. One mass is capital M, the other mass is 1 kilogram over r square. Am I right? So G equals G over r square. So this is going to be an expression for the gravitational field strength at a distance r away from a mass capital M. Okay. So now coming to that earlier question. Gravitational field around me. Yes, there is a gravitational field around me. If you want, you can find the gravitational field strength at a distance 1 meter away from me, which will be g into my mass divided by r square. But that is going to be an extremely small value because capital G is 6.67 10 to the power minus 11. So that is going to lead to a very small gravitational field strength. So if I am to make a significant gravitational field strength, my mass has to be bigger. Understood? So heavier people have a stronger gravitational field around them comparing to thinner people, lighter people. Okay? Their ability to attract is more. Gravitational attraction. Okay, listen. So guys, going back to the previous question a bit, one thing I missed. Now, listen, we found out, as per the calculation, there is a force of 439.7 newtons, or let's say 440 newtons on the person. We found it, right? 440 newtons. That is the force exerted by the earth on the man. So then, that's not a one-way force, no? The same force is also acting on the earth in the opposite direction. Newton's law of gravity is a couple of forces. There is attractive forces between two objects. If A is pulling B, B is pulling A. Okay, so if you are standing on the earth, if the earth is exerting a force of 440 newtons on you, in return, you are exerting a force of 440 newtons on the earth. Am I right? Correct? So that force is acting at the center of the earth in the opposite direction. But when you jump out, you fall. The earth doesn't come to you. You don't attract the earth. The earth attracts you. Reason?
Because we weigh nothing compared to the earth.
Yeah, your mass is 60 kilograms and the mass of the earth is 6 into 10 to the power 24 kilograms. Okay? By any chance, if you can bring all the animals and all the people to one point of the earth, okay, and if it is going to make some sort of considerable mass compared to the mass of the earth, and if you all jump at the same time, then you can expect the earth to come towards you. You understand what I'm saying? I repeat that statement again. When you jump, you fall down, the earth doesn't come to you. The reason because your mass is extremely negligible. Okay? Extremely negligible compared to the mass of the earth. So what I told is, if you can bring all the people and all the animals to one point of the earth, and if you can somehow make a mass which is somewhat closer to the mass of the earth, 6 into 10 to the power 24 kilogram, I don't know what is the population required for that. Okay, if you can get that, and if you all can jump at the same time, then yes, the earth will get attracted. Earth will also get attracted to the people.
Will it jump out of the orbit?
Yes, will it?
Yes.
Not really. Now, we'll come to that later. Why is this Earth is attracting, orbiting around the sun is because of the sun's gravitational force. Sun's gravitational force is extremely higher. Okay? So mass of the earth, mass of the sun is, if you take the entire solar system, if you take all the planets, all the moons, everything, that total mass is still lesser than 1% of the earth, mass of the sun. Okay? If you take the entire solar system, the mass of the sun is more than 99% of the entire solar system. So this 6 into 10 to the power 24 kilograms that we are talking about the earth, that plus the other huge planets, there are planets bigger than the earth, okay, heavier than earth, and all the moons, all the satellites, natural satellites, everything put together, the comets, everything put together, the total mass will be still less than 1% of the mass of the sun. So he is a bigger player in this Milky Way. But still he is not the biggest player. There are bigger players than him. Okay? So Milky Way is just one galaxy. and there are billions of galaxies. There are much bigger stars than sun. Okay.
So G is constant for all those stuff.
No. I'm talking with this G is a universal constant. Correct.
That means like it's applicable in this place.
Now, actually, whether it is a universal constant, I don't think so. For this galaxy, it is a constant. But to what I have seen, I have never come across calculations where they speak about calculations of other galaxies. So you can consider this to be a universal constant. Right. Let's take this down. Okay. Back.
The object exerts gravitation, its own gravitational pull in every direction.
Towards it.
That's
So does that mean that objects with low mass like photons don't experience gravity?
There are no objects with no mass. I mean, insignificant. Smaller the mass, lesser will be the force. There is no object with no mass.
Photons and stuff.
Photons, no, we don't speak about a gravitational force on that. Right. Right, no question. Calculate the gravitational field strength. Calculate the gravitational field strength. At a point 2.5 meters away from a 5 kilogram mass. The answer. G mo r square. Are getting 5.336 into 10 to the minus 7 newtons per kilogram. So you can see, if you just take a normal object, 5 kilogram, its gravitational field around it is It's very insignificant. Write down the next question. 2. Earth has a mass of 16 to 10 to the power 24 kilograms. And a radius of 6,400 kilometers. 6,400 kilometers. Full stop. Calculate the gravitational field strength at. Calculate the gravitational field strength at. Part A. The surface of the Earth. Part B. 100 kilometers above the surface of the Earth. Part C. 1,000 kilometers above the surface of the Earth. Okay, so guys, this calculation is to show you how when you go away from the Earth's surface, the gravitational field strength will decrease. So part A is when you are at the surface of the Earth, the gravitational field strength is given by gm of r square. So that will be gm of r square when you're at the surface of the Earth. G is constant, m is 16 to the 10 to the power 24. Over the r will be the distance from the center of the Earth to you, which is basically the radius. That will be 6,400 into 1,000 square. Am I right? Correct.
So what's Newton's in this area?
Kg ms minus 2 kilogram. F equals ma. F is Newton.
So we can write down the units for G as meters per.
Yeah. So that is why gravitational field strength and gravitational acceleration have the same values. Okay. Right. Guys, then this is when you are at the surface of the Earth. So part B, when you are 100 kilometers above the surface of the Earth, listen. So when you are 100 kilometers above the surface of the Earth, what is the distance between you and the center of the Earth? 6,500 kilometers, right? From the center of the Earth to the surface of the Earth, 6,400 kilometers. And you are another 100 kilometers above. So the distance from the center of the Earth to you is 6,500 kilometers. Correct, right? So now the second part, the R is going to be 6,500 kilometers. And see what are you getting?
Hudson Bay, Canada, the gravitational field strength is like 8 newtons per kilogram or something.
I don't think so.
Something like that.
No.
Several
To what I know, Sri Lanka has the lowest center gravitational field strength. Yes. And did you hear that news? I mean, that was on news recently.
Yes.
Sri Lanka has the lowest gravitational field strength. I think somewhere in down south, a particular point that has the lowest gravitational field strength on the Earth.
Yes, 9.37.
Yeah, you can Google and check.
So what other factors that contribute, I mean, other than the radius?
Nothing else, only those two.
No, but then that down south point doesn't have a high elevation, right?
No, not like that. If you take, we don't know what is the status of the Earth in that part, right? So maybe, I'm just saying an example. There can be a cavity in the Earth which makes the mass around that area to be lesser. Okay, so maybe the center of mass is shifted towards the other side. So it depends on how the mass is distributed within the Earth. So our calculation that we are making here, based on the assumption, the mass is uniformly distributed in the Earth, but practically it's not.
Maybe that area is very
Less dense,
very-
correct, less dense material. That should be the reason.
So I have a question. Let's say you're in deep space where there's microgravity, and let's say you are there, like with a space suit and everything, and also like rat or something. Let's say the rat
Uh-huh.
jumps very high, then will you attract the rat? You don't carry
Come again, I didn't get the first part of the question.
both you and a rat are in deep space with microgravity. Let's say the rat jumps very high, you know, with the gravity.
Yeah,
Then
correct.
you will attract.
Yeah, definitely. Correct. Makes sense. Part C. So guys, part C is your how many kilometers away? 1,000 kilometers away. So then what is the distance between you and the Earth, center of Earth? 7,400. So what is the answer you're getting? 7.31. So this shows you, further you go from the Earth's surface, the gravitational field strength will decrease. So when I say further, don't expect to climb four-story building and tell, okay, the gravitational field strength is lesser here. I'm talking in hundreds and thousands of kilometers. So the part B, I told 100 kilometers away. So when you go 100 kilometers away from the Earth's surface, from 9.77, it has gone down to 9.47. So this is not applicable for your 50 meter, 100 meter. When you go up, the gravitational field strength will be almost the same, 9.8. Understand? Right. Right. So when you go 1,000 kilometers above, it's 7.31. Okay. Right in the next subtopic. So, as you know, on the moon, what is the gravitational field strength? 1.6. So, gravity on moon, the gravitational field strength is approximately 1/6 of the gravitational field strength on Earth. So you can find the mass of moon, the radius of the moon. Okay, you can Google and find those values, and you can use G equals GMO R² to find the gravitational field strength on moon. So it will be something closer to 1.6 newtons per kilogram. Okay. Right on the next subtopic, gravitational potential. Gravitational potential. We'll do one small question before that. Page number 45. Do A part 1. The dwarf planet Ceres is the largest object in the asteroid belt. Where is this asteroid belt? After mass, good. How many of you know that? Okay, wait, just tell me. You all did your O levels, right? Good. So guys, tell me the distance increasing from the sun. Distance increasing from the sun. Tell me the order of the planets. Mercury, Venus, Mars. There's no Earth right here. Where is Earth? Tell me the correct order.
Pluto.
Wait, Pluto, wait, man. You just started with. Tell me the order. Mercury, Venus, Earth, Mars. Wait, Mars. Okay. Neptune. Is Pluto a planet? Yeah. Is Pluto a planet? No. It's a dwarf planet. So now the first four that you told, okay, they have a solid rock base. Do you know that? Made of rocks. The other four are gas. So now between the solid base and the gas base, there is this belt. That is what you call the asteroid belt. Okay. So the dwarf planets are there. What are comets? Yeah, icy dust, icy snowballs are comets. That is there in your O-level textbook. Take the O-level textbook and read. Okay, fine. The dwarf planet Ceres is the largest object in the asteroid belt. Ceres has a mass of 9.38 into 10 kilograms. It has a circular orbit of radius 4.14 into 10^11 meters around the sun. Show that the gravitational force exerted on Ceres by the sun is about this much. Gravitational force. Mass of the sun is given. So guys, now listen. The sun is here. Now this dwarf planet is orbiting around the sun. So now this fellow has a mass of 9.38 into 10^20. Sun has a mass of 1.99 into 10^30, which is a million times heavier than the Earth. Earth is 10^24. This is 10^30. So this is the mass of the sun is a million times, 10^6 times heavier than the mass of the Earth. Do you understand that? Fine. Anyway, this force between the sun exerting on the planet, this dwarf planet, that is what providing the centripetal force required for this dwarf planet to go around the sun. Okay. That is what providing the centripetal force. The question is, show that the gravitational force exerted on Ceres by the sun is about this much. So all you need to do is F equals G m1 m2 over r square. G is 6.67, 10 to the power minus 11. Mass of the sun is 1.99 into 10 to the power 30 into mass of the planet is 9.38 into 10 to the power 20 divided by the distance between them is 4.14 into 10 to the power 11, and that needs to be squared. I'm getting 7.26 into 10 to the power 17 newtons. Okay, have we got this answer? Right. We'll come to the part 2 a bit later, but you can do the part B on the next page. Mercury is the smallest planet in our solar system. The gravitational field strength at the surface of Mercury is 3.7 newtons per kilogram. It is claimed that the gravitational field strength at the surface of Ceres is less than 5% of GM. Evaluate whether this claim is accurate. The radius of Ceres is given. So guys, let's check whether we'll first find what is the gravitational field strength in this planet, which is G equals Gm over R square. 6.67 into 10 to the power minus 11. Mass of this planet is 9.38 into 10 to the power 20. Over the radius of the planet is 470 kilometers, that is 470 into 1000 meters, and that needs to be squared. So the gravitational field strength on this planet I'm getting 0.283 newtons per kilogram. So what is the statement? It is claimed that the gravitational field strength at the surface of Ceres is less than 5% of G. So let's first find what is 5% of G. 5% of Gm will be, Gm is 3.7. 5% of that will be 0.185. That is 5% of Gm. So the statement is gravitational field strength at the surface of Ceres is less than 5% of Gm. Is the statement correct? No, statement is wrong. Ceres has a gravitational field strength 0.283. 5% of Gm is 0.185. So it's other way around. Gravitational field strength at the surface of Ceres is more than 5% of Gm. You can write the conclusion. Claim is incorrect.
That's gravity exists without like the force of the earth.
Right there.
Otherwise, this would be earth would explode.
Hold on. Turn to guys, page 68, question 38. Bring your math skills out. O-level math skills. Page 68, question 38.
So why is R capital?
It's simple. No harm. I just took it.
I'm just asking because normally right is simple.
No, it doesn't matter. I just took. Anyone got 3.37 into 10 to the power 6 meters? Very good. Okay, so the idea behind this is the Earth is 9.3 times more massive than Mars. The gravitational field strength at the surface of the Earth is 2.6 times greater than the surface of Mars, and calculate the mean radius of Mars, where the mean radius of the Earth is given. So guys, listen to me, don't just copy it. G equals G more R square. So now we are talking about two planets, Earth and Mars. So for the two planets, the radius is different, mass is different, gravitational field strength is different. But I know this G is a constant for both. Correct? So if I get the capital G subjected, that is GR square over N. Correct? So what I have done here is, my plan is to get the GR square over F of GR square over M of Earth and GR square over M of Mars and equate it. That's my plan. Because capital G is the same for both. So which means this GR square over M is the same for both planets. Am I right? Right. So that's my plan. So mass of the Earth is 9.3 times the mass of mass. ME is equal to 9.3 into MA. Gravitational field strength on the Earth, GE is equal to 2.6 times GA. Correct? Told in the question. So now, then I wrote this one based on what I just told you now. GR square over M should be same. So GE into RE square over ME is the G based on Earth. Based on mass, GM into RM square over MA. So I have equated those two. Do you agree with that equation? Do you have a question? I have taken the GR square over M of Earth equal to GR square over M of mass. Correct?
So you say 9.3 times more massive than the mass, will it mean that mass of the Earth?
The Earth is 9.3 times more massive than mass. Yeah,
What
mass.
is the word massive?
Mass.
Mass, not radius.
No. Massive. That comes from the word mass. Okay. So 9 GE into RE square over ME equals GM RM square over ME. Correct? Now I'll use this. ME is 9.3 ME. So this ME I have replaced with 9.3 ME. And the GE is 2.6 GM. I have replaced it with that. Now on either sides, this GM will cancel off with this GM. This MM will cancel off with this MM. So what are we left with? 2.6 over 9.3 RE square is equal to RM square. Okay. Agree? So RM is what I have to find, the radius of mass. So if I take the square root, it will become squares will cancel off. RM is equal to square root of 2.6 over 9.3. Square root of RE square will be RE again. So this is the relationship I'm getting between radius of mass and radius of Earth. Radius of mass is equal to square root of 2.6 over 9.3 radius of Earth. Substitute the RE, you get the answer. Okay. Is it too much maths for you? Baby stuff, no man. Too much for 2 marks, true. But the thing is, that is also nice in a way. I know when you do the exam, around 70% of the people will not get this with exam tension. Okay, you're very good at panicking. You don't know to handle some pressure. So when you go to the exam and when you see something like this 9.3 times 2.6 times, you think it's an extremely hard physics question, but it's a very simple maths question. But since most of you people will not do it, it's good in a way that you're going to lose only 2 marks. Okay. I think exactly that is the same reason. Even the examiner has allocated only 2 marks for this. So imagine just allocating about 5 marks for this, gone. No? Fine. Take it out. How many of you panic in situations like not only exams, I'm asking in general? When an unusual situation comes, how many of you panic? Not exam is one thing. Now, let's say you just wake up in the night and you just realize out of your room, someone has come. Okay. How will you react? Someone has, okay, a thief has come. How will you react?
Take a bat and kill him.
Take a bat and kill him. Okay. Now, what will you do? Will you panic in a situation like that? Now, guys, just if you want to go a long way, okay, in whatever your career, listen, one thing that you have to improve as a person is you have to be calm. Whatever the situation, try to be calm. Okay? Don't let your emotions make decisions. There is a lot of things. I mean, I have noticed in lot of people, even after growing up, sometimes you don't have that calmness. Okay? If you are not calm, what the situation that you see is not the real situation. So if you can't control yourself, okay, you are already a bit behind successful people. So that is something that you have to improve as a person. If you are naturally not calm, try to be calm. Don't be reacting too fast. You don't have to react immediately. Those immediate spontaneous reactions that you make, that can make a long-term impact. Okay, if you see some people have, just an example I'm saying. Now some people end up in jails for 7 years, 10 years. Okay, that is not because of they have intentionally made a mistake. That spontaneous anger, that spontaneous decision making, that is not good. So if you want, just take a bit of time, take a minute or two, just calm down, and then make your mind clear, and then make decisions. Okay, not only for exams, at any point, that helps you to go a long way in any career, whatever you become. Okay, if you want to do it good, if you want to do it right, first thing that you need to improve is patience and that calmness. If you are not calm, you are not actually unlocking your true potential. Fine. The next one.
So,
Yeah.
here's a question.
Yeah. Anything related to physics?
Yeah, related to physics.
Yeah. Tell me.
It's asking if the person is drowning.
Hey, that is stupid. No, that is not relevant. Yeah, that is also actually you have to be calm only. Like die calm.
Anyway, drowning should be calm. If you panic, you will.
Yeah, exactly. Yeah. That means you are going to die faster.
The fast death is good because the second.
But if you die faster, then you will start to be safe.
Okay, guys, write down the next subtopic. Gravitational potential. Gravitational potential within brackets 5. 5, the letter 5.
So these people can come with like different number of names and calculations and questions, but they can't come up with different symbols. We
No, I
use the
told-
same thing for work function.
Calm down. Calm down. Gravitational potential, the letter is 5. Okay, tell me what is the symbol you want.
Some other things, sir.
Okay, tell me
It's
some
like
other.
they have different shapes, like 2 circles or something like that.
2 circles. You mean something like this? That looks very wrong.
No,
What
sir,
are
like
they
one inside the other, sir. One inside the other.
One inside
Like
the other.
Audi logo, like Audi logo.
That looks even ugly. I mean.
Okay, sir.
Fine. Right, guys. It is the amount of. I mean, why do you want everything to be in circles, Yusuf? So, or maybe we can come up with something like this here. No? That's okay.
Yes, sir, that'll be better.
So what about an octagon?
It is the amount of work done. It is the amount of work done. When bringing a unit mass It is the amount of work done when bringing a unit mass from infinity to the point. Okay. So what is defined as the gravitational potential at a point is, now let's say guys, there's a mass m, okay, and at a distance r away from it, the gravitational potential at this point's gravitational potential means, if you are to bring a unit mass from infinity to this point, the amount of work that needs to be done is what is defined as the gravitational potential at that point. Okay. The amount of work done when bringing a unit mass from infinity to that point is what you call the gravitational potential at that point, which is as an equation given by phi equals minus gm over r. There is a minus sign. Minus gm over r. M is the mass, r is the distance from the mass. G is once again the gravitational constant.
Sir,
I will tell the meaning of the minus sign a bit later. Take it down with the minus sign for now. And the unit of phi is the work done per unit mass. The work done is joules. So per unit mass means joules per kilogram.
so in this case, will we be using the minus in the answer or no?
I will tell you when to use and when not to use. Done? Write down a question under that. Calculate the gravitational potential. Calculate the gravitational potential caused by the Earth. Calculate the gravitational potential caused by the Earth at the distance of a geostationary satellite. At the distance of a geostationary satellite. Which orbits at a height h of 35,800 kilometers above the surface of the Earth. The radius of the Earth is given 6,400 kilometers. Okay, so guys, gravitational potential is given by minus gm over r, right? Minus gm over r. So the r will be the distance from the center of the Earth to the satellite. Okay, satellite is 35,800 kilometers above the surface of the Earth. So the distance from the center of the Earth to the satellite will be the radius of the Earth plus the height above the surface of the Earth, which is 6,400 plus 35,800. That is 42,200 kilometers is the R. Am I right? So with the minus sign, minus 6.67 into 10 to the power minus 11 into the mass of the Earth is 6 into 10 to the power 24 kilogram over the distance you need to take from the center of the Earth to the satellite, 42,200 kilometers. To convert it into meters, 10 to the power 3. No. That gm over r square is gravitational field strength. here I'm talking about the gravitational potential. There's no square involved in that. It's just minus gm over r.
So you use the minus.
You use the minus. Here you use the minus.
Yeah.
If you want to find the gravitational potential at a point, you give it with the minus sign.
Instead of pi value is b. Okay.
Ah, that's a good question. That is because of a small economic Armageddon.
I was about to ask the same thing, sir. I was like, now you're comparing to velocity.
No. Electric potential is given by V, no. So that I have just used V. Gravitational potential is denoted by phi. Okay. We'll take a small break. See you in 15 minutes. Right, guys, write down the next subtopic. Gravitational potential energy. Gravitational potential energy. Cool. Now, when you in smaller grades that you have learned something called gravitational potential energy and MGH. You have learned something, right? MGH. Yeah, you remember that equation? What is that MGH? What's MGH? Is it gravitational potential energy or what? Listen to me. Now, MGH is never the gravitational potential energy. MGH gives you the change in gravitational potential energy. Now, if you lift an object, okay, its gravitational potential energy will increase. If you lower an object, its gravitational potential energy will decrease. By how much it change? Sorry. By how much the gravitational potential energy change? That is what given by the equation MGH. And also remember that equation is applicable only when it is closer to the Earth's surface. Okay. Now, what we learned today, G will keep changing as you move away from the Earth's surface. Okay. Now, you can't find by how much the gravitational potential energy will be changing by using the equation EP equals mgh if you are lifting an object from the Earth's surface to a height of 1000 kilometers. Why? G is not the same. The G at the surface of the Earth and the G at 1000 kilometers above the Earth's surface is not the same. So if you are using MGH, what are you going to use for G? You can't use 9.81. Understand? So remember the first thing that you have learned MGH as changing gravitational potential energy, that will be applicable only for smaller values of H. Maybe something 2 meters, 5 meters, 100 meters, maybe 1 kilometer, maybe. Yeah, that's fine. But not in hundreds of kilometers or thousands of kilometers. You can't use this equation. Is that clear? And on top of it, MGH never gives you the gravitational potential energy. It gives you the changing gravitational potential energy. Get that clear? Fine. So what is gravitational potential energy? At this level, what is gravitational potential energy? Is the energy possessed by an object due to its position. So we spoke about just before the break, what is gravitational potential at a point now. So if you know the gravitational potential at a point, and if you have kept a mass at that point, gravitational potential energy of that mass, gravitational potential energy of the object at that point is going to be the gravitational potential at that point multiplied by its mass. Okay, I repeat, gravitational potential energy of an object at a point is the gravitational potential at that point multiplied by the mass. Is that clear? Right under that. Gravitational potential energy of an object gravitational potential energy of an object at a point gravitational potential energy of an object at a point is a product of the gravitational potential at that point and the mass of the object. gravitational potential energy of an object at a point is a product of the gravitational potential at that point and the mass of the object. So guys, let's say there is this mass with a mass of capital M, and at a distance r away from it, there is a mass of simple m kept there, let's say. So we know at this point, the gravitational potential at this point is given by phi equals minus dm over r. At a distance r away from the mass capital M, the gravitational potential is given by minus dm over r. Okay, so the gravitational potential energy of this object at this point will be given by minus dm over r multiplied by the mass that you have kept at that point, which is minus dm over r multiplied by simple length. Take it out.
So when are you gonna teach us about the significance of the minus?
Take it down for now.
Okay.
Okay. Write down a question. An object of mass 500 kilograms is resting on the surface of the earth. An object of mass 500 kilograms is resting on the surface of the earth. Calculate its gravitational potential energy. Calculate its gravitational potential energy. So the data given are mass of the earth is 6 into 10 to the power 24 kilograms, and the radius of the earth is 6,400 kilometers.
Is that nothing given in the data sheet?
Okay. So guys, potential energy is given by minus gmm over r. So capital M, the mass of the earth will be 6 into 10 to the power 24. Simple M, the mass of the object will be 500 kilograms. Over the r is the distance between the object and the center of the earth, which will be the radius of the earth, that is 6,400 in kilometers. Convert it into meters.
Sir, the mass of the earth, does it include us all standing on it or with all the buildings and everything, or?
No, without that. But if you
So how do they come up? It's not like they have weighing scale or something, right? So-
no, that can be calculated. If you
Because there are
take,
different mass,
what is
like
the,
different
what is the
materials
bulk?
and all. Right?
Hold on. 7 into 7 billion, 8 billion, they
Yeah.
have increased now.
So now India is the most populous one.
8 billion, 8 into 10 to the power 9 is a population. Average mass of a person,
60, 70.
70, let's say. 7 into 8 is 560. 5.6 into 10 to the power 11 kilograms if you take the mass of all the people. Whereas we are talking about the mass of the earth is 6 into 10 to the power 24 kilograms. So that is
Yeah, so
still,
that's nothing.
the
Yeah.
ratio is 10 to the power 13 times. The mass of the earth is 1 millions of million times bigger than the mass of all the people. So if you consider the mass of all the people, that is extremely small compared to the mass of the earth. So you don't have to consider that.
Oh, yeah.
Okay.
So we only consider non-living parts of the earth, right? We don't consider plants or animals.
No. Okay, what is the answer you're getting? With minus 3.13 into 10 to the power 10.
So why is it mine? Then we can see mine.
Can. Patience.
It's only applies considering that the two objects we are talking about are the only objects within
Yeah, correct.
certain area. Otherwise, the interference from other objects is also
Correct, but it will not be that significant. It's a small impact.
No, if a third object is much more massive, then it will be huge.
You're talking about something massive than Earth around Earth.
Yeah, I mean, so this is not only one. This is anyway.
Yeah, correct. It has to be isolated. Right. Write the next question. Okay, to answer your question, what was your question? Can the energy be minus? I'll answer that after this, okay? Write the next question. An object of mass 800 kilograms. An object of mass 800 kilograms is taken away from the surface of the earth an object of mass 800 kilograms is taken away from the surface of the earth to a height of 1600 kilometers above the surface of the earth. Above the surface of the earth. Full stop. Calculate the change in gravitational potential energy of the object. Calculate the change in gravitational potential energy of the object. Okay. So guys, now listen. There was an object on the surface of the earth, and it is taken to a height 1600 kilometers above the surface of the earth. What will be the change in gravitational potential energy of the object is the question. Correct? So what you need to do is find its initial gravitational potential energy when it was on the surface of the earth, and find its final gravitational potential energy when it is lifted 1600 kilometers above the surface of the earth, and get the difference in the two values. Okay, take it up. What's the answer? Minus or plus? So E1, you take the initial energy minus G M over the R will be 6.4 into 10 to the power 6 meters when it is at the surface of the earth. Then E2 will be minus GM minus GMM over R, where the R will be now 1600 kilometers above the surface of the earth, means from the center of the earth, the distance will be 6400 plus 1600. That is 8000 kilometers, 8000 into 10 to the power 3. And then you take E2 minus E1, final minus the initial. It is becoming a positive value, which is 1.0 into 10 to the power 10 joules. Or is it different? Are you getting this? It's a positive value, not minus. It has to be a plus value. Why? Because when you lift an object, its gravitational potential energy will increase or decrease? Increase, right? So, when you do this calculation, if you have done it right, you have to end up with a positive value. Gravitational potential energy is increasing. So, the delta EP has to be a positive value. So, when will you end up with a negative value? When you take an object downwards, then the change in potential energy will be getting as a negative value. Okay, now listen. Whereas the gravitational potential is taken to be 0 at infinity. Gravitational potential is taken at 0 at infinity. So the gravitational potential energy of an object is 0 at infinity. So at a point before infinity, the gravitational potential energy is supposed to be less than that. So which will be a minus value. Okay, which will be a minus value. So by definition, if anyone is interested to know why it is minus, by definition, what is gravitational potential at a point? The amount of work done. The amount of work done in bringing a unit mass from infinity to the point. But if you take two masses, the force between them is anyway attractive. Listen to this carefully if you want to know why it is minus. But it's not a must for you to know why it is minus. The force between them is anyway attractive. So you don't have to do an external work to bring that object here. The work is done by the field itself. So you don't have to do externally. You don't have to do a work externally to bring it here. So what is by definition the gravitational potential? The amount of work which needs to be done in bringing a unit mass. But you don't have to do a work. Work is done by the field. So that's why it becomes minus. Understand?
So for electric field, why external minus?
Because in that case, sometimes the force is attractive, sometimes the force can be repulsive.
Gravitational potential energy is not a very stable form of energy.
Meaning?
That's why objects fall down in order to convert it to another form, because it's not stable.
What do you mean by stable?
Like gravitation, it's not convenient to have long term, right? So when you
No, it depends. If the forces are balanced, it can stay. Now, if you take a satellite orbiting this Earth, its gravitational potential energy will remain constant.
I mean,
It depends on the forces acting on it.
But like, it feels a little unstable. Even if it can.
Yeah, that depends on the forces acting on it.
So when you go away from the Earth's surface, the gravitational potential
Increasing. Potential energy is increasing. When you go away from the Earth's surface, if you go away, you're lifting it up, right?
Yeah,
Okay.
Lifting up.
Mm.
See, gravitational constant.
Mhm.
Towards the surface.
Gravitational potential, you mean?
No, not the potential.
Okay. Mhm.
Towards the surface, it increases.
You mean the gravitational field strength? Gravitational constant is a constant.
Yeah, the constant is the field strength. Towards the surface, it increases.
Grav- gravitational constant?
No, field strength.
Okay, gravitational field strength increases. Correct. Okay.
So, why is it the potential? Why is it?
No, gravitational potential by definition, what? The amount of work needs to be done. So now if you, this is, let's say for an example, 100-meter mark. This is for an example, let's say 200-meter mark. So the amount of work that you need to do to bring it here, the work done is what you call the gravitational potential at those points. Okay. So now the work that you need to do is, let's say, to bring it here is 100 joules. So the gravitational potential here will be minus 100 joules per kilogram. So to bring it here, let's say the work needs to be done is 200. So the gravitational potential here will be minus 200 joules per kilogram. Okay. So when you see the difference between the two, the difference between it's minus 100 minus 200, that is plus 100. So when you move away, the gravitational potential will increase, or the gravitational potential energy will increase. Tell me, what is your question? We have an unanswered question. So that depends on the definition what they have created for gravitational potential. Okay, fine. Anyway, guys, page number 87, question number 50. Page number 87, question number 50. Okay, right. Part B on the next page. A satellite is launched from the surface of the Earth into an orbit, a height 5 RE above the surface of the Earth. The gravitational potential energy delta E of a mass m when it experiences a vertical displacement delta H can be calculated using the expression delta E gravitational is mg delta H. State why this expression cannot be used to calculate the change in gravitational potential energy of the satellite. I already answered this. Usually we use delta E, the change in gravitational potential energy is mgh, right? I told you that will work if it is closer to the Earth's surface. For 50 meters, 100 meters, 200 meters, you can use that. But if you are going hundreds of thousands of kilometers away from the Earth's surface, I told you, you can't use this equation. What is the reason I told you?
Because
it
it
is
has a different gravitational force.
gravitational
Field
field
strength.
changing. Am I right? So exactly that is what they have asked you here. The change in gravitational potential energy of a mass m is given by the equation delta E equals mgh. State why this expression cannot be used to calculate the change in gravitational potential energy of the satellite. So if you see the satellite, it's going from a height from the surface of the Earth to a height of 5 RE above the surface of the Earth. So that means if the surface of the Earth is 6,400 kilometers, this is going 5 times of that, which is 32,000 kilometers above the surface of the Earth. So at such a height, definitely the gravitational field strength is different. So for a 1 marker, they have asked to write the answer. G is not the same at such a height. It keeps decreasing when moving away from the Earth. It keeps decreasing when moving away from the Earth. Okay. Calculate the change in gravitational and potential energy of the satellite. Mass of the Earth is given. Radius of the Earth is given. Mass of the satellite is given. Complete this question at home. Part 2. Find the final kinetic potential energy when it is at the orbit minus when it is at the surface. That difference will be the answer. And also try to mark a few more. There's question 46. Part A and B. Sorry, part A, 46, part A. Yeah, that's enough. See you next week. There's a bit more theory to be done to answer the questions in the future.
So next week I have in class.
What?
Next week I
Yeah,
have in
yeah.
class.
Yeah.
It's like what, the 27th, right?
You properly wake up and come to the class. Okay?
So I'll be traveling, sir.
Good.
I'll be in Medina.
Okay, there is class. Okay.
6:30 also I have to get up, sir.